when we first made the organoids, we thought we had a very interesting scientific tool. For the first time, we had genetically stable cells in the dish. And we were hoping for a lot of things that were predictive for patients, etc. So the surprising thing that happened to me actually was probably that it actually was true. So initially we were hoping a lot of things when Toshio Sato made the first organoid. And now in these meetings 15 years later, all of these things are actually coming true, much more in that sense than we might have expected. So indeed, those initial organoids do seem to be a patient-specific tool that we can use in all these different applications.
One time I was doing a screen and I saw all these immune cells just come into one of the tissues. I've never seen this before, what's going on? And it turns out I had a contamination, which was not a good thing, but it helped us to see that our immune cells really trafficked into organs as they should. And so now we do injuries where we can actually elicit that immune response. That's not a contamination, but it's, you'll see the immune cells come in, they'll go right to the site of injury, do their repair mechanism, and we can do it with drugs as well that elicit the immune response. But it was really nice to see that if we are vascularizing all our organs and having this circulation, that you're still seeing what you see in the body, whereas if you have an injury or even if you have an infection, contamination, the immune cells just go right there and take care of it, and it's just exciting to see in a Petri dish.
When you give a targeted inhibitor, one of the things that happens at the level of the transcriptome is that pathways go the opposite direction. You get lots and lots of transcripts for a pathway that has been shut down. And so then unraveling those types of what is actually happening in the tumor can be hugely beneficial for then identifying which of the drugs do we want to pick for it. So if you've got a tumor that is dysregulating purine biosynthesis and you have a purine analog that it's synergizing, it may not be the best hit in your screen, but you have a molecular basis by which to say this is how this is working. And those types of surprises where you're just this is backwards, I don't understand, and you have to sort of bang your head against the wall for a bit are more and more common the more you look at individual tumors.
I was really surprised about how quickly the cells would invade. So previously I worked with glioblastoma rather than small cell lung cancer. So glioblastoma or GBM is incredibly invasive, but working with small cell lung cancer, they just attack immediately and invade into these organoids within a matter of hours. So, it doesn't even have to be 24 or 12 hours, it can be less. So I think that just speaks to how quickly they can invade in a patient's organ and why there's such a significant unmet need for this patient population.
I remember the first patient we derived organoids from. It was a young man with cholangiocarcinoma, widely metastatic. He said, "Hey, I want to donate my cells to you to grow organoids." And so we were fortunate to get these and grow them from him. And when we put them into mice, what was really interesting is that the organoids had a tropism. They would go to the exact spot where we isolated them from and grow very nicely, but they wouldn't grow in other parts of the body. And even if you injected them in the vein or in the belly or by any different methodology, what you'd actually find is that some way they would find their way back to the niche that they liked and grow. So it's always been something really fascinating to me, this kind of memory that these organoids have, especially not only memory from a human to a mouse, that they retain that. It's something that always strikes me in terms of just how special these organoid cultures are and just how much we have still to learn from them.